We are looking at graphing functions, and we're looking at, in this chapter, functions that you need to be aware of and what the shapes look like. And this will be a library of functions. Sometimes you'll hear this called the parent function. We're going to be getting into transformations of graphs in the next chapter, next section, and it's helpful to know what these parent functions look like. The other thing we're going to look at is piecewise functions. So these are functions that have multiple equations, and depending on what the domain is, depends on which equation you use. So a lot of situations in life, if an equation is representing that situation, a lot of times it's more than one equation that represents the situation, not just one equation. Other thing we're going to be looking at is using transformations of graphs to help us graph in the next section. Okay, so there are these functions that you should be aware of and what the graphs look like. And a lot of these, I'm sure you know exactly what they look like. So if I have f of x is equal to c, this is called our constant function. And this is where c is equal to a real number. So you should know what f of x equals c, f of x equals a constant looks like. Another way to say this is y equals c. And so y equals c, we would find c on the graph, y equals c, and we would have a horizontal line that goes through that. You should be able to explain properties of these graphs. So looking at this function, notice that our domain is all real numbers, so we don't have any trouble spots. Our range is only going to be that y value, c in this case. Notice that this is never increasing or decreasing. This function is always constant. And that's what we say if we're looking at intervals where our graph is constant, we're looking at the graph where is that horizontal. The other function that you should be familiar with is called the identity function. And this is, I'm going to use function notation, f of x equals x. So if we're graphing this, whatever we put in for x, we're going to get back the same thing for y. So 0, 0 is a point, 1, 1, 2, 2, negative 1, negative 1, etc. And so we get this diagonal line. So properties of this graph, the domain again is all real numbers. The range is also all real numbers. Notice that this is strictly increasing. Okay, so the next one is our quadratic equation, our squaring function. So this is going to be that f of x equals x squared. If we graph this function, it's a parabola, it faces upwards, and that vertex is at the origin. So here, our domain is all reals. But the range, so looking at this, notice the y values that we're hitting. The smallest y value that we hit is 0. So our range starts at 0, including 0. So have a bracket around that 0, and then that infinity. If we were looking at the intervals where it was increasing and decreasing, we got it's increasing on the interval from 0, starting when x is 0, to infinity. It's decreasing. It's going downwards, left to right, from negative infinity until we hit 0. We have an x and y intercept. At 0, 0. We have our cubic function. This is if f of x is equal to x cubed. So if we have f of x is equal to x cubed, the general shape is going to look similar to this. So domain and range, all reals. This is strictly increasing. And again, we have our intercepts at 0, 0. We have the square root function. So this is f of x equals the square root of x. So this is where our domain has to be limited because we have that radical. And it's even powered, so x has to be greater than or equal to 0. And the graph kind of looks like a half sideways parabola. So our domain is 0 to infinity. Notice that's also our range. We're never going to have negative y values. And so our range also, we hit 0 and going to infinity. Strictly increasing. And intercept at 0, 0. We have our cube root function. Kind of looks like our cubic function, but it doesn't grow as fast. It's growing at a slower rate, so it looks more like this. And so this is f of x equals the cubed root of x. Strictly increasing, domain is all reals. And same thing with our range. We're hitting all the real numbers. Negative infinity to infinity. This graph is strictly increasing. And intercept at 0, 0. We got the reciprocal function. And so that's a reciprocal function. This is f of x equals 1 over x. So we got to be careful here because we can't have values of x which set our denominator equal to 0. So we have to restrict that domain to exclude x equals 0. If we look at the graph of this function, the graph is in the first quadrant and looks similar to this. And a reflection across the origin. So our domain and our range are the same because we're hitting all the numbers except for 0 for both the domain and range. So we got negative infinity all the way to 0, but not including, and union 0 to infinity. And since we weren't including 0, we put a parentheses on that piece. Notice that we're going down from left to right here. We're also going down left to right here. So this is decreasing from negative infinity to 0. It's not defined as 0, and then 0 to infinity. I forgot to mention, some of these things have symmetry, and I had mentioned it for this one, but I forgot to mention it for the other function. So this one is symmetrical with the origin. And we were talking about the other day that if something was symmetrical with the origin, it was an odd function. So if you go back up to our cubic function, you can also see that and the cube root function, those are also symmetrical with the origin and they're odd. Square root function, that doesn't have any symmetry. Go back to this cubic. So cubic, we also said, maybe I should just say it's odd, which means it's symmetrical with the origin, I guess. Notice our square root function, that one is symmetrical with the y-axis. And that was an even function. So symmetrical. With the y-axis. And it's even. And the identity function, we can also flip this and make across the origin. So folding our paper in force is how I think of it. And it would lie on top of each other. So this is also odd and symmetrical with the origin. And if we're going to continue to talk about symmetry, notice our constant function. F of x equals a constant. If I folded that across the y-axis, it's symmetrical. So this is symmetrical with the y-axis. So it's even. So there's one other function, which is called the greatest integer function. So let me pull that up. Okay, so the greatest integer function. I'll show you how they write it. So f of x equals, it's kind of like a double bracket on each side. So this is equal to how we define this. This is equal to the greatest integer less than or equal to x. So just to recall what an integer is, we're coming in from negative infinity in a pattern, -3, -2, -1, 0, 1, 2, 3, going off to positive infinity. So if x is an integer, then it is going to equal itself. If x is not an integer, you're going to look at the integer that falls directly to the left of it. So it's kind of confusing because it says greatest. So maybe you would think it's higher than that, but it's the greatest integer less than x. So for instance, if I had 1/2, if I was starting to plot points here, if I had 1/2, that's not an integer. So I would think to myself, what is that integer that falls directly to the left of that on the number line, which is 0. Any number in between 0 and 1, not including 0 and 1, will always give me back 0, right? So if I had 0.1, I'd have 0. If I had 0.2, I would have 0. If I had 0.9, I would have 0. Once I hit 1, that's an integer. It's going to equal itself 1. And so if you look at this, it's like a step. And I think that's another name for it, a step function. So if I have 0, it's equal to itself 0. If I have any number between 0 and 1, not including, I'm going to get back 0. So I have this horizontal line here. And at 1, I have an open circle at 1, 0. Because at 1, I actually get back 1. So any number that falls between 1 and 2, the integer that's smaller is, or to the left of it, is going to be 1. So I'm going to have a horizontal line from 1 to 2 with an open circle at the point 2, 1. When I hit x equals 2, that's an integer, and so it's equal to itself, so that's equal to 2. So anything from 2 to 3, or in between 2 and 3, integer to the left, greatest integer to the left is always 2. And then at 3, we're going to jump up to the y value of 3. So if we think about it, negative numbers. So if I have -1, anything in between -1 and 0, that's not an integer, is going to give us to the integer of -1. Let's see how this looks like, kind of a step function. If we're talking about domain are all real numbers. We got to be careful though with the range. Notice the range here. We don't have any numbers that aren't integers, right? All of our y values are integers. We don't have any y values in between those integers. And so when we look at the range here, it's a set of integers. And so if we wanted to write that in set notation, I would just have that curly bracket and I would denote that it's, coming in. So I'd do the ... -3, -2, -1, 0, 1, 2, continuing in that form. So I put that ... So our domain, like I said, we can put any number in there and it's going to spit out a real number. So our domain is -∞ to infinity. So one other function you need to be familiar with is the absolute value function. So f of x equals the absolute value of x. The shape of that is a V. Domain is all real numbers. Our range, though, we're not hitting any negative numbers. The smallest value, y value we have is 0. So 0, including it to infinity. We're decreasing from -∞ to 0 and increasing from 0 to infinity. And this one is symmetrical across the y-axis. Which means that it is an even function. So this actually was a perfect one to stop with, the absolute value function, because that actually can be defined as a piecewise function. And that is another thing we're going to talk about in this section. So piecewise functions. If I was looking at that f of x equals the absolute value of x, a way to define this well, if x is a positive number or a 0, right, I would get back the same thing I plugged in. So if x is greater than or equal to 0, the number we're plugging into that absolute value spits back the same number we plugged in, right? That makes sense. So if I plugged in 0, absolute value of 0 is 0. If I plug in 1, absolute value of 1 is 1. It's the same number I'm plugging in here for x. If it's a negative number, if x is less than 0, In order to get what the absolute value of that number is, we're taking the negative of that result. So let's say I have -1. To get the absolute value of -1, I have to take the negative of that number, which would give me the positive. And so this has two different equations, and it depends on what the domain is for that piece. So let's look at another example of a piecewise function. Let's say we want to graph f of x is equal to, let's say 2x minus 1. And this is if x is less than -2. How about 4? If x is between and including -2, and 2 not including. And how about x squared if x is greater than or equal to 2? So depending on what number we're plugging into the function depends on which equation we're going to use. What domain does it fall into for that piece? So for instance, if it asked you to find f of -5. Well, x equals -5, I would see which inequality that is true with. If I plugged it in, is -5 less than -2? Yeah. -5 doesn't fall between -2 and 2, and it isn't bigger than 2. So this tells me to use equation 1. Because -5 is less than 2. And so if I'm going to use equation 1, wherever I see an x, I'm going to plug in this -5. So we have 2 times -5, which is -10, and then -10 minus 1, which gives us -11. So you should be able to answer any question they throw at you to find a value. So if they said find f of 7, I would go to my function and figure out which piece does that fall into, that inequality that makes it true. Well, that would be the third equation, right? 7 is greater than or equal to 2. So we're going to use equation 3. So f of 7, to find that, we're going to plug in 7 wherever we see an x in equation 3. So we're going to square 7, which gives us back 49. Okay, so to graph these, I do them kind of in pieces, and you just need to make sure that you don't extend that graph past those values of x that represents that equation. And so let's look at the first equation and graph what that is. And if you look at it, 2x minus 1, and that's a linear equation, so you know about what's going on with that graph. So you have some sort of idea. So you always want to find out what is that point at the end value of our inequality, even if it's not defined there. And so notice for my first equation, these are our values which are strictly less than -2, but I actually want to see what's happening if I plug in -2 into that first equation. And that value I get is actually an open circle because I'm getting really, really close to that point, but not getting there. And so let's look at that. So if we're plugging in values to the piece f of x equals 2x minus 1. I want to always, again, look at what's happening at the end value of my inequality, even if it's not included. So I want to plug it in here, -2 and for x. So that gets me 2 times -2, which is -4. -4 minus 1 is -5. And I'm going to just put a little note to myself, open circle. So now let's just choose anything that's smaller than -2, and we can plug it into this equation. So if I plug in -3, I got 2 times -3 is -6. -6 minus 1 is -7. So I have enough to know what's going on and to graph that piece. Do it up here more. So at -2, I saw that I had -5, but it was an open circle. At -3, I have -7. It's a closed circle. Anything less than -2 is going to be on this line. So that's just equation 1. And notice again, I didn't extend this for values of x greater than -2 on this line. That's usually where students get mixed up. They extend the graphs farther than the domain of that equation. So if I look at equation 2, well, that's just a constant. And so if I'm plotting points, any number I plug in between -2 and 2, not including 2, I get a y value of 4. So I always want to see what's going on the end values of my inequality. So let's plug in -2. If I plug in -2, I get back 4. It's included with that equation. So this would be a closed circle. But if I plug in +2, it's going to be an open circle at 2, 4. So -2, 4, we had a solid circle. And then at -2, a +2, 4, we had an open circle. And any number in between there would give us back 4. So this is a horizontal line. So one more piece, which is that third equation. And those are for values which are greater than or equal to 2. And that equation is x squared. So if I plug in my n value of 2, it's included because it's greater than or equal to 2 for that piece. Plug it in for x, I get 2 squared, which is 4. And this is a closed circle. I notice this is x squared, it's a parabola, so I have the general shape, but I can plot another couple points if I wanted to. So 3 is bigger than 2, 3 squared gives me 9. Okay. So notice that 2, 4, I say I have a closed circle, but for the second equation, 2, 4 was an open circle. So this actually closes this circle up for this piece. And then at 3, I have 9. And it's a parabola shape. There. So we graphed the piecewise function. We answered some questions about particular values of x and what y we would get back. You should also be able to look at your piecewise function and answer questions like what is the domain and what is the range. In order to get the range, a lot of times we'll have to graph it first so we can see what's going on. The domain, though, it basically gave us what our domain is. It tells us we're going to use all values of x which are less than -2, everything in between -2, including -2, but not 2, and everything greater than or equal to 2. So our domain are all real numbers. That piecewise function, and just look at it, the inequalities, and that would give us what the domain is. The range, though, this is where we got to be careful. So notice we're not hitting all the y values in this graph. There's a jump of y values that we're not hitting. We're not hitting any y value that is between -5 and 4. And it looks like I'm not even hitting -5 because that's an open circle at that piece. And so the range, I'm coming in from -infinity. I hit all the y values until I get to -5, not including. So -5 with a parentheses, union. So now the next y value that's smaller, but above that is 4. So 4, I'm including 4 because that's a y value. So put a bracket, so 4 to infinity. You should be able to, after you graph it, look and tell me where is this graph increasing, decreasing, and constant. So if I look at where is it increasing, so going up from left to right, always starting with the smallest to the largest. And we're looking at x values. And so notice that this first graph to the left, that line, that's increasing. So these are all x values coming in until I hit that -2. And it's an open circle. So I'm going to put a parentheses. So we have from -infinity to -2 parentheses union. So notice that it's also starting to increase when x is 2. This is going upwards in here. So x values is going to be 2 to infinity. Decreasing, it's never going down. And then constant. So which pieces of the graph are horizontal? Well, I see we have a horizontal piece. Because it's a solid circle and we're starting there, I'm going to say including -2. But I'm stopping, it's changing direction. I'm stopping at +2 with the parentheses. So I tend to like these, and the fact that it shows me, how to graph a lot of different things. It also shows me that we can come in and you can tell me domain, range, increasing, decreasing, constant. These are also piecewise functions are ones that you're going to see a lot when you get into calculus, because where it's changing equations, things could be happening. We could have a jump in a graph, meaning it's discontinuous, which notice we do have a jump in our graph when x is -2. So it's discontinuous there. And we don't have a jump in our graph at x equals 2 because that one equation filled in the circle, closed circle of the open circle. And so it is continuous from -2 to infinity. But if there had been a jump in there, once we changed 2, then it wouldn't be continuous there. Let me see if you guys have any questions. So the next example, we want to graph the piecewise function f of x equals the equation 1 over x if x is strictly less than 0, and the equation cubed root of x if x is greater than or equal to 0. Besides graphing, there's a couple of other questions they wanted us to find. They asked us to find the domain of each function. In this case, I'm only giving you one example. So find the domain. We want to locate any intercepts, and we want to graph this equation, and based on the graph, find the range. If I want to find the domain, again, I can just look at my inequalities and see what are the x values I'm hitting. Well, I'm hitting everything less than 0, but then I'm hitting 0 for the second equation and to infinity. So I'm hitting all my x values. So my domain is going to be all real numbers. I would probably just start graphing it. So I know that 1 over x, and we kind of just looked at that family of functions, what that looks like when x is less than 0. That was that piece that was in the third quadrant that looks like this. If you didn't see that though, you could start plotting points, right? But this time you're choosing values which are less than x. X less than 0, choosing values of x which is less than 0. The problem is we cannot plug in that n value because that n value, x equals 0, makes this undefined. But if I plug in -1, 1 over -1 is -1. If I plug in -2, I get -1/2, -3, I would get -1/3. If you plug in any number that is between -1 and 0, those are going to blow up. So like if I plug in -1/2, 1 over -1/2, that flips it, which gives me -2. If I did -1 over 100, that would give me -100. So we have this shooting down to -infinity as we get closer and closer to 0 on the left. So then we want to graph x, and f of x equals the cubed root of x. So I want to see what's happening at the n value. If I plug in 0 here, I get the cubed root of x, which is 0. And this is a closed circle. So at 0, 0, I have a closed circle. Anything bigger, so the cubed root of 1 is 1. I would probably put in numbers that I know how to take the cubed root of. So the next one, perfect cube, will be 8. Would give me 2. I know what the general look of this looks like too. So at 1, I have 1, and at 8, I have 2. So it looks similar to this. So if I'm looking at the range, even though there's a jump in here on my graphs, I'm hitting all my y values. So the first equation, 1 over x, is hitting all the values from -infinity up to 0, but not including 0. And then the second equation, that's hitting all the y values from 0 to infinity. And so our range are all real numbers. The intercept is at the origin. And again, you should be able to answer questions about what intervals is this increasing, what intervals is this decreasing. From left to right, I see it's going down from -infinity to 0. Increasing, that's the second equation. Because it's a solid circle and that's where it starts, and it's not where it's changing direction right at that value, I'm going to use a bracket. So from 0 to infinity. Okay, so our next example, we're actually going to be given the graph of the piecewise function, and we were going to want to find what that piecewise function is. And so let's say that we have a point at 0, 0. I'm moving to the left. I have a point at -1, 1. And the graph is decreasing from -infinity to 0. The next one, we have a point at 1, 1. We also have a point at 0, 2, except it's open. And we have a point at 2, 0, and it's closed. So it looks like this. So find the piecewise equation. Piecewise function. That satisfies this graph. Well, notice both pieces are lines. Great review for your end of the chapter test too for this weekend. So you shouldn't be able to find equational lines. And so equational line, we need two things. We need a point and we need a slope. Well, looking at this, we have multiple points. And I can look at that and I actually can tell what my slope is, right? Rise over run. I'm actually falling 1 and going over 1 to the right. So rise over run, falling 1 is -1, 1 to the right is 1. We actually even have the y-intercept there, right? That y-intercept is 0. And so the equation for this one on the left is y equals our slope, -1 times x plus 0, or just y equals -x. So that's our first equation, -x. And we need to look at for what values of x does this hold true for. I mean, these are values that our x is less than or equal to 0. Because this was a solid circle. Okay, so for that second line, one to the right of that first one, -x, I can also see, I am looking at a point. I am, again, falling 1, going over 1. So again, I can see that my slope, those should look like they're kind of parallel. Yeah, so those really should look parallel, as my scale is -1. My B value, well, if it was included, but where it would be crossing that y-intercept, right, is at 2. So my equation for this line, that piece, is y equals -x plus 2. Okay, but I got to be careful in what values of x we're including for that equation. So it has to be bigger than 0. And it has to be less than or equal to 2. So this would be a case where this piecewise function is not defined for all real numbers. That domain is not all real numbers. The domain would be negative infinity all the way to x equals 2. If I was looking at the range of that, notice that I'm not hitting any values of y below that x-axis. I am hitting 0, and I'm hitting all the y values above that x-axis. So it'd be 0 to infinity. Looking at that, that's decreasing everywhere. I would say negative infinity, I'd probably stop it at 0. And then I would say 0 to 2. So last example on this section, unless you guys have any questions, is if f of x is equal to that greatest integer function of x divided by 2, we want to find the following. So the first one wants us to find f of 1.2. All this is doing is telling us to go in to our function, wherever we see an x, we're going to plug in that 1.2. So if we do that, we have this greatest integer of 1.2 divided by 2. Okay, so before we take that greatest integer, we're going to simplify that down, 1.2 divided by 2. Well, 2 goes into 1.2 0.6 times. So 0.6 is not an integer. So I have to go smaller than 0.6, but the biggest integer less than 0.6. And so the biggest integer less than 0.6 is 0. So for the second one, same idea. This time we're plugging in 1.6 wherever we see an x. So we have 1.6 all over 2, and we're taking the greatest integer of that result. Well, if I divide 1.6 by 2, that gives me 0.8, which is also not an integer. But the biggest integer smaller than 0.8 is also 0. If we go in and we plug in negative 1.8 wherever we see an x, we get negative 1.8 divided by 2, and then take the greatest integer of that result. So 2 goes into negative 1.8, negative 0.9 times. Negative 0.9 is not an integer, but the integer to the left of that is the biggest, is going to be negative 1. Let me see if you guys have any questions. If not, that is going to be the end of this section, and we'll take a break.